Today we're going to talk about impulse and the conservation of momentum. And so let's review a little bit. Here's what we did last time, and some of what I'm going to talk about today is kind of a repeat. But this is Newton's second law, as we explained it, months ago. If you apply a net force to an object, that object will accelerate. And the net force and acceleration will be in the same direction. They are directly proportional. If you double the net force on an object, you double the acceleration. But the amount of acceleration depends on the mass of an object. The more massive it is, the more inertia it has, the harder it is to move. And so it's a resistance to net force. You can kind of think of it that way. Well, if we keep this all like to averages and not worry about instantaneous values, what is acceleration? Well, the average acceleration is how much I change my velocity over a given time. It's delta v over delta t, change in velocity over change in time. Right? Okay. So now if we rearrange this a little bit, this is what we did last time. We said if I apply a net force on an object for a period of time, that will equal the mass times the change in velocity of the object. Well, mass times velocity we have a name for mass times velocity, right? We call it momentum. And so momentum, we use lowercase p to represent momentum, because it would be really a difficult equation if it was m equals m times v. Wouldn't work. It'd be confusing. So for lack of a better letter, everybody just got together and agreed to use the lowercase p to represent momentum. Equals mass times velocity. Well, notice what we have right here. We have mass times a change in velocity. So the mass times the change in velocity is really a change in momentum. If I have an object and its mass is staying constant, but I change its velocity, I have changed the momentum of that object. There are situations where the mass changes over time and the velocity stays constant, but we're not going to be dealing with that today. So we have this neat little expression that's very easy to derive, and yet very, very profound. The net force applied for a period of time is equal to the change in momentum. Now, we have a name for this. This is called impulse. When you apply a net force to an object for a period of time, the product of that force times time gives you what we call impulse on an object. And that's equal to the change in momentum. Well, in this whole thing right here, the fact that an impulse, force times time, equals the change in momentum of an object, this is called the impulse momentum theorem. And it's kind of a big deal in physics. It's really a profound idea, as we're going to see in a little bit. Of course, one thing we did last time is we rearranged this again, kind of going back to where we started. We said that the net force equals the change in momentum over the change in time. And this right here is how Isaac Newton defined the net force, or defined his second law. His second law included the product of mass times velocity. But if you simplify it, if you stipulate the mass doesn't change with time, it turns into F equals ma. So anyway, that's kind of what we did last time. Now, the units for impulse, well, by the way, sometimes you'll see impulse abbreviated with the, or represented by the letter I, capital I, with the vector hat on top. Some books use it, some don't. We're going to use capital I later in the year for this thing called rotational inertia. So it can be a little bit confusing, but that's, that's okay. You can use that if you want to. Now let's think about units. Well, if I look at impulse, it's a product of force times time. So that's newtons times seconds. But when I look at change in momentum, it's mass times a change in velocity. That's kilograms times meters per second. And these two sets of units are equal to each other. Because after all, what is a newton? It's a mass times an acceleration. Kilogram meters per second squared. If you multiply that by seconds, you get kilogram meters per second. So, yay, the universe works. So, when do I leave my answer in Newton seconds, and when do I leave my answer in kilograms meters per second? If I ask you for an impulse, how much impulse was applied to the object? Leave your answer in Newton's times seconds. However, if you write your answer in kilogram meters per second, I'm not going to mark it wrong, because it's not wrong. It's just a little inappropriate, but not wrong. And just as much, if I ask for a change, calculate the change in momentum of an object, and you leave the units in Newton seconds, I'll be mildly irritated, but I won't take any points from your score. But the best units to use are kilogram meters per second. So impulse is a product of net force and time. Okay? Is a product of net force and time. Now, we dealt with other quantities that are products before, and we've graphed them, like work. Work is a product of force and displacement, right? Remember when we graphed force as a function of displacement, and the area underneath that graph was work? Or we graphed velocity as a function of time, and the area underneath that graph of velocity as a function of time was displacement, because force, velocity times time gives you displacement. So we're going to do the same thing here. We're going to do a really simple problem that you would never actually do it this way, but let's try it. Let's see, an example. Let's do an example. A net force of 5 newtons to the right is applied to the object for 4 seconds. What impulse was applied? And maybe we've got like a little cart on wheels and keep it real simple, and here's our net force that's applied to it. It's pulling it to the right, and we're, for a few seconds. Well, you would say, okay, given, well, the net force is given to be 5 newtons, and delta T is given to be 4 seconds. We want to find the impulse. We said the impulse is equal to force times time. So you would say 5 newtons times 4 seconds equals 20 Newton seconds. Put a box around your answer, and we're done. Easy. But I'm going to do it another way, which is kind of stupid. But if I do it this way now, it makes other things a little bit easier. Let's graph it. So 1, 2, 3, 4, 5. This is force in newtons. And then time in seconds. 1, 2, 3, 4. Now, what's true about this problem? Well, the force is constant with time. So the force is 5 newtons at the beginning, at 1 second, at 2 seconds, at 3 seconds, at 4 seconds. So it's just a horizontal straight line. And something is constant when you graph it as a function of some other thing that is constant with respect to. It's just a horizontal line going across like that. Easy. And notice something. If you look at the shape that this graph makes a rectangle. And what is the area of this rectangle? Well, that's 4 seconds times 5 meters. It's 20 Newton seconds. Each one of these little squares, if you picked out a little square and just brought it out here, well, each square underneath here has a height of 1 Newton and a width of 1 second. 1 times 1 is 1, so it has an area of 1, but the units, it's not meters squared or square inches or any of that kind of nonsense. It's newtons times seconds. So each little box here represents 1 Newton second of impulse. So the area underneath here represents impulse. So the total area of this is impulse. And impulse is equal to the change in momentum. Now, by the way, it's not equal to momentum. It's equal to change in momentum. Make sure you understand that. People think, oh, the momentum is 20. No, the change in momentum is 20. Now, if the object had an initial velocity of 0, then its final momentum is 20 kilogram meters per second. And then if you know the mass, you can figure out what the velocity is. Okay. So this is kind of silly. I would never actually do this problem with this graph because it's kind of unnecessary. But what if I had a graph, okay, that looked something like that. Now, let me show you something here. I'm going to change the momentum of this little foam rubber ball. Now, I'm going to do it in regular motion, okay? I'm going to go boom. Right? So what did I do? I moved it. Right? I changed its momentum with a force. Force times time, I gave an impulse to it, it changed the momentum of the ball, and it rolled away. But if I look at it in slow motion, you can kind of think of this as like a baseball bat hitting a ball or something like that. When it comes in, there's no force, there's no force, there's no force, there's no force. Then contact is made. When contact is just barely made, there's hardly any force. But then as it moves in, it squishes the ball in. It hasn't had time to move out of the way yet. And then, so the force acting on the ball goes way up. And then the ball starts to rebound off my hand and starts to spring back, and then it moves away from my hand, and then once it leaves contact with my hand, the force is 0 again. So the force is not constant with time. 0 force, then it ramps up to some maximum, and then it ramps down back to 0. So you might have a situation like this where if you were to graph the force as a function of time, you might have 1, 2, 3, 4, 5. And time 1, 2, 3, 4. Let's go ahead and do 5. And this is time in seconds. Now, by the way, this could be time in nanoseconds or milliseconds or something. If it's like a baseball bat hitting a baseball, the contact time is not very high time. So it's probably in thousandths of a second. But let's just keep it easy, all right? So I'm just going to leave it in seconds. And let's say that you hit something with a net force, and it ramps up like this. It goes from 0 force to a maximum of 4, and then for 2 seconds it stays at 4, and then you get a rebound, and it gradually leaves contact, and the force goes back to 0. Well, the impulse is a product, right, of force times time. But now force is a function of time, and it's not constant with time. It varies. Now, if you know what the expression is, if you have an analytical function of force as a function of time, and you want to find the area underneath that graph, you could do formal integration, right? If you're in calculus, you can integrate. But many of you are not in calculus, but it doesn't matter. We can still figure out what the product of force and time is by looking at the area underneath the graph. So we got this triangle, we got this rectangle, and we got this triangle. And we can just add them up. And I think you guys just did a take-home test problem where you did something similar to this. But it wasn't force as a function of time, it was a function of force as a function of position. So the area underneath that graph was work. But the area underneath this graph is not work. It is impulse, which is equal to the change in momentum of the object. So I'm going to say 1/2 the base times the height plus the base times the height of the rectangle plus 1/2 the base times the height of the little triangle. So let's plug in our values by looking at the graph. The base here is 2 seconds. The height here is 4 newtons. Then you look at the rectangle. That is a base of 2 seconds and a height of 4 newtons. And then plus this little guy right here has a base of 1 second, or 1/2. It's 1 second and a height of 4 newtons. And now we can just add them up. This is 4 Newton seconds plus 8 Newton seconds plus 2 Newton seconds, which gives me a total of 14 Newton seconds of impulse acting on that object. Now, if I told you what the mass of the object was, let's say it was, 1/2 kilogram, well, then you can figure out what the change in velocity was, right? Because this is equal to 14 kilogram meters per second, which is my change in momentum. So the object that I applied this force to, you would say, well, its change in momentum is its mass times its change in velocity is equal to 14 kilogram meters per second. And if I told you that like the mass was 1/2 kilogram, well, if I divide both sides by 1/2 kilogram, the change in velocity is 28 meters per second. So we increased its speed by 28 meters, or we changed its velocity anyway by 28 meters per second. If it was, if it started with an initial velocity of 0, it would be going 28 meters per second after these 5 seconds, applying a force like this. And there's no other way to do this problem, right? It would be hard to do this with energy. It would be, because you don't know the displacement. It would be hard to do with, well, you can't do it with kinematics because the force isn't constant. So the acceleration isn't constant. So you can't use your kinematic equations to figure out, the final velocity. But you can use impulse and momentum, and it works really well. Okay, so that's one kind of problem, an impulse problem where I give you a net force on an object. If you If it varies in time, great, just graph it, figure out the area underneath the graph, that'll be your impulse, and all will be well. But now we're going to talk about conservation of momentum. So slightly different topic. Oh, wait a minute. Oh, yeah. Okay. Conservation of momentum. And this is so easy, but it's really profound. So let's take a look at where we started. The impulse momentum theorem. We have the net force on an object. We multiply it by the time that that object is applied, and that will be equal to the change in momentum of my object. Now here's an example of this. Very simple example. Imagine I have a crate on wheels, and I apply some force to it, and it turns out that this force is the net force on the object. Okay, and we could say that maybe the object has initial velocity, so v naught is not equal to 0, but we can see that, hey, this force applied for a certain period of time, do you see that this force, everybody look, this force is going to increase the speed, right? If it's going to the right and I pull it to the right with even more force for a period of time, that object will have a final velocity that's greater than the initial velocity. So therefore, it will have a greater momentum. It's momentum change. Mass times velocity is momentum. So greater velocity, same mass, means greater momentum. So we changed its momentum by applying this force. But what if F net equals 0? So we're looking at the same situation here. Here's my crate. There's no friction or anything. It's got some initial velocity, but there's no net force on it. Now you know what to do here. You know what's going to happen to this cart. What's the final velocity going to be after a few seconds? It's going to be 0? Yeah, it's going to be the same as the initial velocity. Do you see that the velocity of this guy is not going to change? Because there's no acceleration. There's no net force. I mean, yeah, we got gravity pulling it down. We got a normal force pulling it up. It's not on an incline or anything. And we're pretending like there's no friction or air resistance. So, essentially, in our little magical world, this thing will go on forever. Now, let's think about it, and now you're getting a little glimpse into how theoretical physicists think. Because they look at that, they think about this, and they go, well, we've got this impulse momentum theorem that we got from Newton's second law. Well, what happens if the net force is 0? Well, what is 0 times delta t? Equals 0. But that is my impulse. I have 0 impulse, which means I have no change in momentum. Well, what is delta p? It's the final momentum of my object minus the initial momentum of my object, right? Anytime you have a delta, it's a final minus an initial of whatever that quantity is. Which means that P final minus P initial equals 0. So what does that tell you about P final and P initial? They are equal. P final equals P initial. If and only if the net force is 0. This is huge. This idea. If you have an object and the net force on the object is 0, the momentum is not changing with time. The momentum is conserved. That's what we mean by conserved. It's not changing with time. Like we had conservation of mechanical energy in Unit 6. The mechanical energy, you have something up here, it equals the mechanical energy over here. All right, well now, it's really obvious with something that's this simple. But I'll show you something that's a little bit more complicated. And yet, it is the same. It all depends on your system. Really, the net force is 0, on your system. Well, in this case, the system is my cart. There's the force of gravity in the cart, but we got a normal force canceling out that gravity. Here we have a net force. Oh, the momentum will change. But here, okay, yeah, we got a force of gravity like this, but there's a normal force like this that's canceling it out, and therefore there's no net force on the object. Therefore, the object's momentum is conserved. It's constant. But what if I'm playing pool or something? Or shuffleboard? Or better yet, curling. You ever watch curling? I love curling. The little sweeper. Okay, they're changing the coefficient of friction in front of that puck when they're sweeping. But anyway, actually the physics in curling is actually quite complicated. Let's keep it really super simple. Let's say we have an object 1. This is before. And here's object 1. It could be just floating in space. But it's moving. It's on the move. Okay. And here's object 2. Could be a different mass. But it's at rest. Before. Now that means initial, right? So this has M1, M2. Let's say the masses don't change with time. And this is V1, the velocity of 1, initial. And then V2 initial equals 0. So say it's at rest. It doesn't have to be at rest. I could do this with, Then they collide. Wham! They hit each other. Smack. All right, so let's take a look at what's going on while they're colliding. Here's object 1. Here's object 2. Now, they are going to apply forces to each other. Here's the force of 1 on 2. Right? But what did Newton say? What does his third law say? For every force on one object, there must be an equal and opposite force on another object. So this is the force of object 2 on object 1. And, Newton said they're equal but in opposite directions. And here's how we say it. Force of 2 on 1 is equal but in the opposite direction. Hold on a second. I made a mistake. Leave some space. I'm going to do something here in a minute. Is equal. So leave some space here. The force of 2 on 1 is equal but in the opposite direction of the force of 1 on 2. Okay, but here we come to a part that confuses students sometimes, but it's so obvious. These forces are being applied to these objects at the same time. Does that make sense? Bam! They hit each other. this finger is going to be the force of 1 on 2. This will be force of 2 on 1. Bam! Okay? Now, instead of using the word bam, I really should be using the word time. The amount of time that this force is applied to object 1 is exactly the same as the amount of time that object 2 has this force on it. Yes? Doesn't that make sense? So I'm just going to make everything average. And so I'm just going to say, okay, I'm going to multiply it by the time that these forces are applied. But what is the force of 2 on 1 times time? What is force times time? Oh, by the way, this is my system right here. There are no outside forces. There are no net outside forces acting on my system. These might be cue balls rolling on a pool table. Sure, there's gravity, but the normal force cancels it out, and all that sort of thing, right? Or we can just imagine two things in empty space hitting each other. So there's no net outside force acting. They hit each other with equal and opposite forces for the same amount of time. Well, what is force times time? Change in momentum. So this is the change in momentum on object 1. And that's going to be equal, but in the opposite direction as the change in momentum of object 2. See, object 1 gets its momentum changed. Object 2 gets its momentum changed. But those changes in momentum are equal and opposite. Okay, well, let's do this. Let's add this to the other side. I just added this to the other side, and I get this expression. When you add the change in momentum to object 1 to the change in momentum of object 2, I get 0. Which means overall, if this is your system, there is no change in momentum overall. Yes, object 1 changed its momentum, but object 2 changed its momentum with an equal and opposite change. So overall, in your overall system, the momentum is conserved. So this, when you go through everything, becomes this. The final momentum is equal to, well, you know what, I'll just go through it. This is kind of tedious, but I think it's worth going through. Okay, let's do this. Delta P1, what is that? That's M1 V1 final minus M1 V1 initial, right? That's the change in momentum of object 1. Its final momentum minus its initial momentum. Then we're going to add to that delta P2. Well, that's M2 V2 final minus M1 V1 initial. I'm sorry, I got my subscript, V2. It's M2 V2 initial. So this is the change in momentum right here. So this is the change in momentum of object 1 plus the change in momentum of object 2 equals 0. Well, let's keep all the finals on this side. I get M1 V1 final plus M2 V2 final. This is going to be equal. Well, add this to the other side and add this to the other side. I get M1 V1 initial plus M2 V2 initial. Well, if those two objects are my whole system, when I add the momentum of object 1 plus the momentum of object 2, that's my total final momentum of my whole system. And that's going to be equal to my total initial momentum of my system. In other words, when two objects collide, they conserve momentum. The initial momentum of the system is equal to the final momentum of the system, just before and just after a collision. And I have an example of that. You guys have played with this in my class. Now, here's the thing. Momentum is not totally conserved throughout this whole thing. But if you look at it just before a collision to just after, I mean instantly before and instantly after, you will see that the momentum is conserved. Now, the reason why there is change in momentum in this system is because as the ball swings up, gravity acts on it as a net force, slows it down, and then gravity acts as a net force and speeds it up. So it hits again. But if you look at just before, look, one ball, it's going to strike this, one ball is going to come off. Let me do that again because I moved it. Now what if I do 2? 2 balls move. I can do 3. 3 move before and after. So the total amount of motion, the total amount of momentum in the system isn't changing. Now it does, they do all kind of swing together because of entropy, and I think one of these isn't lined up perfectly. You can even do 4. Watch. When these collide, 4 will move, but this one at the end will stay because you have to conserve momentum. See, so momentum is being conserved.
We go 5.
Okay. Yes, we'll do 5, and you'll see that momentum is conserved.
Oh, I thought something cool.
So you can have 0 momentum. Hey, just before and just after, there is 0 momentum in this system because this ball has momentum to the right or left. This one has momentum to the right or left, but it's in the opposite direction as this, so it has 0 momentum total when you add it all up, and it stays 0 the whole time.
2 on one side, 1 on the other.
Okay, then you can do this.
Can you do 2 on 1 and 1?
Oh, that's good. We should like do 2 on 1. What would I do?
2 on 1, so there's only 3.
Yeah.
Like, pull 2 from one side, 1 from the other side?
Like this.
No,
No.
one lines.
What?
You pull 2, you pull 1, and you drop it.
Pull 2, pull 1.
Yeah.
Oh, God. I don't know what's going to happen, but I know momentum will be conserved. What? Okay, so, yeah, well, it's hard to lose something that one could argue one never had. All right, so there we go. Now they're all moving. So there's a lot of ways to play with this, but just before and just after each collision, momentum is conserved. And when you play pool or you play shuffleboard or anything like that where things collide, momentum is conserved. Okay, so the key thing is that if you have a problem where momentum is conserved, start with this and then break it down. Look after the collision, where are all the pieces? Usually there's only going to be 2. I think we're only going to do 2 objects at a time. And then after the collision, before the collision, look at where the momentum was, and they have to be equal to each other. And it doesn't matter which one. You can do P initial equals P final, obviously. And then what will happen is that you'll be given everything except one thing. You'll have an unknown, and now you can use algebra to solve for it. But momentum is being conserved. It has to be. And in all of this explanation, this very long explanation, we're developing ideas logically. We're starting off with, the definition of momentum, what changes momentum, net force, that comes from Newton's second law. And then if the net force is 0, well, then you can't have a change in momentum, which means momentum initial equals momentum final. And well, what about a collision? Well, in a collision, you got BAM going on, so that the individual pieces are having their momentum changed, but when you add up all that momentum change, you get zero. Okay, and so one could argue that maybe the total momentum in the universe is zero, because it all kind of went out like that. Well, the initial momentum was zero. By the way, there are people that say, hey, if the total momentum in the universe is zero, and the total amount of energy in the universe is zero, because you have negative energy due to gravitational potential and stuff, well, maybe the universe is just zero, a universe from nothing. I don't know, kind of crazy to think about. Anyway, that was too long, but that is